Roots of complex numbers. So far, we have learned basic operations of complex numbers. For example, we discussed how to add complex numbers, how to multiply them, how to divide them, and some other elementary operations of complex numbers. Now, this topic is going to be our first non-trivial calculation about complex number, where we are going to use those elementary but very important operations. So we are going to find roots of complex numbers. Of course, we need to first learn what is root of a complex number. Or even more elementary question would be, what is root of any real number or integer? So this is not something very new for all of us. So for example, if I consider a real number 4, and if I ask, can we find a real number x such that x square equals 4? Of course, we can find, and the answer is there exists 2 and minus 2, such that when we square 2, we get 4, and when we square minus 2, we also get 4. So, solving such problems, for example, we can consider another question, can we find a real number such that the cube of that real number is 10? And many other questions. So, now we are going to study root finding for complex numbers. In other words, we are going to find u such that u raised to power n is equal to our given complex number z. Now, there are two problems that we are going to discuss in root finding. The first question would be, how many roots there are? So, for example, in our previous simple example where we asked the question, can we find an x such that x square equals 4? There were two answers, 2 and minus 2. So the question would be, how many roots of this problem exist? To answer this problem, we are going to see a very important consequence of fundamental theorem of algebra. So fundamental theorem of algebra has this following consequence, that if we have a polynomial of degree n with complex coefficients, then the equation p of z equals 0 has precisely n solutions. So what is a polynomial? Just a recall, a polynomial of degree n would be an expression of the form an z raised to power n plus an minus 1 z raised to power n minus 1 up to so on plus a1 z plus a0. And all of these coefficients ai's are basically complex numbers, for I is equal to 1 to 3 up to 0 1 to 3 up to n, and this variable z is a complex variable. Now the result says that if we have a polynomial of degree n, then it must have exactly n solutions. So in other words, p of z equals 0 must have exactly n solutions. For example, if I have a polynomial, for example, p of z equals z cube minus 4 plus iota into z square plus 4 plus iota 4 into z minus 4 iota. Now, as we can see that the coefficients of this polynomial, so for example, minus 4 plus iota, it's a complex number. Similarly, 4 plus iota 4 is a complex number, and the constant term minus 4 iota is also a complex number. Now, the next question would be, what is the solution of the equation p of z is equal to 0? So, in other words, what are the roots of this polynomial? Now, we can factorize this polynomial into the following factors: z minus 2 square multiplied by z minus iota. So, in other words, we can say that this polynomial has the following roots: z1 equal to 2, z2 equal to 2, and z3 equal to iota. Now, we can see that 2 is repeated twice. So that's what this terminology counting multiplicities mean. So if I have 2 appearing twice in the factorization, then I would count it as 2 roots. Now let's see how this important corollary of fundamental theorem of algebra helps us in finding how many roots are there of any complex number. Now, if I want to find nth roots of a complex number, then I need to solve the expression u raised to power n equals z. Now here u is a variable and z is given complex number. Okay? So I can write the expression in the following way, and now it becomes a polynomial expression in variable u. Okay, so here variable is u and z is given complex number. And as we know that by fundamental theorem of algebra, a polynomial of degree n must have exactly n roots. And if we are trying to find the solution of this expression, in other words, we are trying to find the u such that u raised to power n minus z equals to 0, then this expression now must have n solutions. So we can say that given a complex number z, there are exactly n nth roots of that complex number. Now, since there are many nth roots of a complex number, this expression now denotes the set of all nth roots of a given complex number z naught. Now, given any real number, let's say r naught, then we know that every real number is also a complex number. And in school, we used to calculate the square roots and the cube roots and tenth roots of any given real numbers. And there we were not bothered about is the answer unique or there are many answers of this question. Now we know that if I want to calculate 10th root of a given real number r naught, then there will be exactly 10 answers. If r naught is a positive number, then there's going to be one answer or one member of the 10th roots of r naught which is going to be positive. And it's that positive number that we used to consider in schools. But the other numbers are going to be complex numbers mostly. So now our aim is to find what are those numbers. So as a matter of notation, when we are writing down r naught inside the square root notation with an n written on it, it means that particular positive nth root of r naught, and it does not denote the other complex answers of this nth root of r naught. Now the next question is, now we know how many nth roots of a complex number are. The next question would be how to find them. First, we need to observe that if we are given a complex number in exponential form, it means z is equal to r e raised to power iota theta. Then here r is the modulus of this complex number. In other words, it is the distance of the point from the origin. And this theta is basically the angle with positive x-axis. And of course, if I increase or decrease this theta, then we will be moving away from this point. And if I increase theta, then I will reach this point. And if I increase more, then I'll reach this point, up to so on. But if I increase theta by 2 pi, then I will be reaching at the same point. So in other words, if I write down this z is equal to r e raised to power iota theta, then this complex number is the same as r e raised to power iota theta plus 2 pi. Now similarly, if I take another round in the counterclockwise direction, then I'll be reaching at the same point again. And if I keep doing this thing, then I will be reaching at the same point again and again. So in other words, we can say that if I have a complex number and if I add integer multiple of 2 pi in this angle theta, then I'll be reaching at the same point. And similarly, if I move in the clockwise direction 2 pi units, and each time I travel a 2 pi distance, I will be reaching at the same point. So in other words, we can say that this k is not just positive, it could be any integer. Now, if I'm given two complex numbers, r1 e raised to power iota theta and another complex number r2 e raised to power iota theta 2. And if we assume that these two complex numbers are equal, then of course their moduli should be equal. In other words, r1 should be equal to r2. And as a first observation, it comes to our mind that theta 1 should be equal to theta 2. But that's not exactly true, as we have observed that if I travel 2 pi units in counterclockwise or clockwise direction, then I'll be reaching at the same point. So in other words, we can say that theta 1 is in fact equal to theta 2 plus 2k pi. So there is a difference of 2k pi between theta 1 and theta 2. Now this observation is going to be used in our root finding. The next simple observation is basically a recall from our previous discussion. If I am given a complex number in the exponential form, then I can calculate its power in a very simple way, just taking the power of r and e raised to power iota n theta. As you remember that we proved this fact by using mathematical induction. Now let's use these observations in finding root of any complex number. Now consider a complex number z0 equal to r0 e raised to power iota theta naught. Here r0 is the modulus and theta naught is the angle with positive x-axis. And the question is, what is z such that z raised to power n is equal to z0? In other words, we want to find nth roots of this complex number z0. Now, taking power of this z0 would give me z raised to power n is equal to r raised to power n e raised to power iota n theta. And z raised to power n should be equal to z0. So this implies r raised to power n e raised to power iota n theta is equal to r naught e raised to power iota theta naught. Okay, so there should be naught here. And so this implies that we have two complex numbers. On left side I have r raised to power n e raised to power iota n theta, and on the other side I have r naught e raised to power iota theta naught. And these two complex numbers are equal. So in other words, their moduli should be equal. In other words, r raised to power n should be equal to r naught, and this implies that r is equal to the nth root of this positive real number r naught. Now here, when I'm writing down this notation, it means it is that one unique positive real number which is the nth root of r naught. R naught is also a positive real number. And the second expression, the relation between their angles would be n theta is equal to theta naught plus 2k pi, and this implies theta naught is equal to theta naught over n plus 2k pi over n, where k is any integer. Now this implies that the value of z is equal to, so this is the modulus of this z, and this is the angle or the argument of this complex number. Okay? So that's how we find the nth roots of given complex number z0. Now here we can see that k varies over the set of integers. So if I take k is equal to 0, I get one nth root. If I take k is equal to 1, I get another nth root, and up to so on. And since we know that there are infinitely many integers, so it seems like we are going to have infinitely many nth roots of a given complex number. Now, but we observe that there are going to be exactly n roots of given complex number. Now, or in our next discussion, we are going to handle this question: what is going to be the variation of k? Okay, so for this, let's first calculate a very simple example. So we are given a complex number 2i, and we want to calculate the square roots of this complex number 2i. So we can write down the complex number 2i in its exponential form in the following way: 2 e raised to power iota pi by 2. Now we want to find square roots. So in other words, n is equal to 2 in this case, and basically we will be solving z raised to power 2 is equal to z0. Now using this fact, we are just going to replace n with 2 because we want to find square roots, and r naught with 2 and angle theta naught with pi by 2. And here we get the answer. Now, when we take k is equal to 0, we get 1 plus iota, and when we consider k is equal to 1, then we get the root to be minus 1 minus iota. Okay, now if I take other values of k, so for example, if I take k is equal to 3, 4, 5, up to so on, then we will observe that we are going to get the same roots again and again. So the only two unique values are z1 is equal to 1 plus iota and z2 is equal to minus 1 minus iota. Now let's explore further about the geometry of these roots, and of course this will help us in finding the conditions on k. When I consider k is equal to 0, then it's going to give me a complex number which is going to be on a circle of radius nth root of r naught. This is the radius of the circle, and we can observe that all of these nth roots are going to be on the same circle. Now let's consider the geometry of these nth roots. So let's say this is the value for k is equal to 0. And when I consider k is equal to 1, then I'll be getting the next complex number, and the difference between their arguments would be 2 pi by n. Okay, so this is the value for k is equal to 1. And similarly, when I consider k is equal to 2, then I'm going to get another complex number, but the distance or the angle, the distance between their arguments is going to be the same as the distance or the difference of the arguments between k is equal to 1 and k is equal to 0. So in other words, we are going to be traveling in a very uniform way if we consider their arguments. Okay, so we are increasing their arguments in a very uniform way. And as we can see that when we will reach k is equal to n, then we have traveled exactly 2 pi units. And according to our observation earlier, we should have reached at the same point as k is equal to 0. So in other words, this value is also for k is equal to 0 and also for k is equal to n. And of course, when we keep on going, for example, when we take k is equal to n plus 1, then I'll be getting the value exactly the same as we get for k is equal to 1. And we can keep on traveling on the same circle, but they are going to be exactly n values. And if we want to simplify the situation, we'll just consider the values of k to be 0 to n minus 1. Because if we consider k is equal to n, then we will be getting the same roots again and again and up to so on. And for a very simple calculation, just consider n consecutive values of k. And for simplification, just take k is equal to 1 to n minus 1. Now, given this roots, the values of z, we denote these nth roots in the following way. When we take k is equal to 0, then we denote it by c naught. When k is equal to 1, we denote it by c1 and up to so on. And we denote these nth roots by ck. So it's just a notation that we'll be using. Now let's further explore the geometry of these nth roots of given complex number. Now we know this expression that these are the nth roots. When we consider n is equal to 2, in other words, consider square roots of a complex number, then these two complex numbers, which are the square roots of a given complex number, lie at the opposite ends of a line segment. And of course, if I change the complex number, then these two complex number will be changed, but they will be always at the opposite ends of a line. And similarly, if I consider cube roots of any complex number, then they lie at 3 vertices of a regular triangle. And similarly, when n is equal to 4, they are the vertices of a square. And if I keep on increasing these values of n, then I'll be getting vertices of a regular pentagon, vertices of a hexagon, and up to so on. So basically, these roots of any given complex numbers, of course, lie on a circle of radius nth root of r naught, but there is much more about those roots, that they are vertices of a regular polygon. We have seen how to calculate roots of given complex number. We also discussed about their geometry.